Okay, so the welcome to the operating systems class, the week 2. And last week, let's little bit preview our last week, and then we will move into our week 2. So during the last week, we studied about the introductory concepts of operating systems. So let me share my screen and go to the modules, module 1. So we know where we were during the last week. Okay, so during the last week, actually, we studied the, as I said, the operating systems, and um, during that session, we introduced the operating system from two basic points of views: uh, resource management and the extended machines. When we talked about the resource management, the operating system's main responsibility is to manage the different parts of the systems effectively. The extended machine view provides users with the abstractions that are more convenient to use than the actual machine. So we talked about, we talked about the operating systems as it mentioned in the chapter 1 of our textbook, and that included a very detailed overview of different components of the operating systems, how the components work very briefly, and also we touch based about different types of operating systems, different flavors of operating systems within the scope of uh, our our course. And then most importantly, we did several hands-on exercises. I mean, during last week, we did, in fact, a lot of hands-on exercises. The first one was to install the virtual box. So basically, we did install the virtual box on our desktop. So something like that, the Oracle's virtual box. And then as a part of lab lab 2, the lab 1 was the virtual box installation. Then we installed the CentOS operating system, Linux operating system. I know many of you are still um, trying to complete that assignment, that exercise. So, if you are still stuck on any of the steps, let me know. We will go through the exercise in detail. There are some certain challenges in the CentOS, with the CentOS, especially with the host key. I mean, the controlling the mouse. I mean, all those things. But if you have, if you still having difficulties, we can definitely schedule sessions. You can schedule session with me, and we can go over the installations in details with you. But what nominally is expected is something like a basic operating system with the CentOS saved on your virtual box. Then in the third part, actually, it was pretty easy. I mean, third lab number 3 was installing the Mint Linux. Pretty much when we are going to use Linux in our within this course, we will be using the Mint Linux with ourselves. With our course, because of its simplicity and ease to use. So the Mint Linux is another flavor of Linux. So we installed two different flavors of Linux. CentOS is basically the free version of Red Hat Linux operating system, while the Linux Mint or Mint Linux, whatever you tell, I mean, it is a very user friendly. Um, they call it very modern. The hacker level operating system. Hacker level means this operating system has all the recent features and used for ethical hacking to ensure that operating systems are secured. That's the purpose of doing the ethical hacking. So those are the operating systems that we installed on our disks. So that was a lot of work that we have done hands-on last week, and then we together worked on the takeaway journal. Basically, what I did is that when I went through the questions that has been asked here and discussed those during the class. Many of you have participated in that discussion and started providing the answer as well, answer keys to it as well, in your own version of explanation. The takeaway journal does not need to be focused on, I mean, all this focused on the specific questions here. It can be a combination of these questions as well as your own takeaway from the lesson, as well as the video, the lecture, and the existing materials, namely the book, as well as some outside materials as well. We also worked on some open source commands. So basically, we picked up certain commands and then we worked on the difference. I mean, we basically discussed about the some basic questions related to the open source software. I mean, the open source software in the context of Linux operating system is extremely important because Linux itself is an open source software, and I mean, it is open source is very important part of the software development, because I mean the proponents of the open source software believe that the software should be um, openly available. Whatever software we are using, we should be able to access its source code, and we should be able to modify the source code and redistribute the source code. I mean, everything related to software, I mean, so the source code should be very open. Here, open does not mean free. I mean, free here, the concept of free here is in the line of like free speech, not the free coffee. So that needs to be kept in mind. I mean, in fact, you can talk, you can discuss a lot about the open source software in, I mean, you can go through a lot of discussions on the open source software from online resources, and I would encourage you to do so. However, I mean that we picked up certain comments on our Linux operating systems, and we discussed about what are those. We in fact we showed you the the manual page of each of this software, and went through a details of that. We also discussed the quiz assignments. Basically, had some overview of the quiz questions, and some of you participated in the question answer sessions for the quiz questions. So this week also we are going to create our, I mean, organize our presentation in along the same line. I mean, we will have some mixture of theoretical background as well as the hands-on experience with the Linux. So in the first hour, let's try to read something, and then in the second hour, we will jump into some hands-on exercises. But we can always switch, and I mean, we can always switch between the slides and the hands-on exercises as we move through the course all the times. We have to remember, I mean, Linux is very extremely hands-on. So we have to start doing as much hands-on exercise as possible. So, and on the top of that, this week actually we have certain programming exercises. We will do that together in the class, and that's pretty much it is. And so, I mean, I'm starting up the Mint Linux on my virtual desktop. We will go. I mean, because
Sir, quick question.
yeah, go ahead, please.
Tomorrow, with tomorrow being the 4th of July, will we have the second lecture on Wednesday? Or
Yes,
what is your plan
yes,
for that?
yes. I did not put together a um, official announcement yet, but yes, we will celebrate 4th of July tomorrow, and we will have our class day after tomorrow. That's on Wednesday. That's a good
Thank you.
question. Thank you.
Thank you.
Yeah. Okay. So that's our Mint Linux, and I just put the username and password. I mean, last week actually we went over the Mint Linux extensively, creating the multiple users in the Mint Linux, and so I logged in, but what did my session go? Yeah, now it shows up. So that's pretty much it is. We will be using it extensively for our Linux command line practices. Anyways, so before we start, do you guys do any of you have any questions regarding the last session or anything anything related to the assignments? I'm still grading those assignments. So what is there any thought? I mean, you will find that as far as the screenshots go, I I gave a lot of, I mean, feedback to your assignments. So basically, always remember that those are not the last time I'm grading those assignments. So you are welcome to correct your assignments and resubmit it, and those will be available for grading again. So if you think that I mean you can do more with the assignments, please do so and submit for further grading. Just drop me a line that you have changed your assignment or you have reworked on your assignments. So basically, what I found from your submissions is that many of you simply presented very brief screenshots. I expected as many screenshots as possible, and also many of you did not provide any reference to any screenshot. I mean, basically included the screenshots in the questions itself. That's what I'm looking for. I mean, maybe you have some issues with installation. I want to see those. I mean, if you need help, I'm available to help you, but we need to get the proper screenshots that I mean, the steps that you went through during the installation process. So that's what we have to do. And if you face any difficulties, like in CentOS, many of you were struggling with the mouse, the mouse icon, all those things. So, I mean, in those cases, just include those as comments during your screenshots that you could not capture the screenshots because of these reasons. But that is important because I mean what I expect is that at the end of the day your CentOS Linux is somehow installed. That evidence should be there. And then if you have faced any difficulties or something happened during your installation that prevented you from installing your CentOS Linux, then let me know on the screenshots itself during the assignment. Uh, you won't be negatively impacted for that, but that will help us to understand the levels of difficulties and also levels of efforts that you put together for that. So that's pretty much regarding the assignments. I mean, that's ongoing, and you are more than welcome to submit your already submitted assignment, resubmit your assignments for further grading or improved grading, whatever you want to do. So that's pretty much about the past week's assignment. So we are going to start a new chapter today from the book. This is processes and threads. I mean, we are really embarking into the uh, basically we are really starting um, we are starting a detailed study on how a operating system is designed and constructed. The most central concept of any operating system is the process. Process is an abstraction of a running program. There is a program, we can write a program. We will see during this class, actually, we will be studying some programs. So that's the operating system. Basically, the concept of the process is abstraction of a running program, and everything else hinges up on this concept. And the operating system designer should have a thorough understanding of what a process is and is. Um, I mean, we have to learn what is a process. Now, we will let's do some introduction first. I mean, processes are one of the very traditional abstractions that operating systems provide. The processes support the ability to have the concurrent operation even when there is only one CPU available. That they turn a single CPU into multiple virtual CPUs. You know, when there are 4 or 8 or more CPUs, I mean multi-core systems, let us say. So if there is a multi-core system available somewhere, there could be dozens, or I mean there could be a lot of processes, hundreds of processes running in those systems. Without the process abstraction, modern computing could not exist. So basically, if we talk about the process, let's just a second. Let me show you some example, like on the Windows machine. You are familiar with the task manager, right? So those are the processes. You see the processes, it says. So these are the processes that are running on this machine. As I am presenting this PowerPoint, I have a lot of Google Chrome sections active. So let's say if I delete some Chrome section, I mean Chrome, so you can see that number of Chrome sessions are, I mean, they are reducing. I'm deleting those behind the scene. So basically, the processes represent the abstraction of the programs that are running on the system, and that is a most important hands-on example using your Windows operating system. Most of us is on Windows machine. If you have any other machine, let me know. We can show the processes there too. But if you are on a Windows machine, then looking at the task manager is the best way to look at your processes. Okay, so these are the processes running on our machine here. So you can see the processes are kind of applications. I mean, application program. The apps are the abbreviation of the applications. And by applications, we mean the application programs. Somebody wrote some programs. Those are used in the Windows operating system. But then there can be some background processes as well. I mean, background processes uh, are running in order to maintain the system or to maintain the applications, whatever it is. So that's an integrated version of the processes. So that's pretty much the representation of the processes. So if you, as I said, if you have multiple cores in your operating system, multiple cores, then you will have a lot of processes, you know. So, so basic definition of the processes are clear, right? I mean, those are the programs basically running in on your system. Now, all the modern computers, as you have one, um, they do several things at the same times, right? Your computer does a lot of things at the same time. Uh, I mean, we work with the computers, but not understand. I mean, about how many things it is doing at the same time. So, uh, first, I mean, if we consider a web server, for example, so a web server is a program, right? I mean, that's an application running on a computer. I mean, our computer may not have any web server, but in theory, the web server is a program that runs on a user's computer. Now, what happens to the with the web server? It's very simple. Like we are going to google.com, that is also running on a web server, hosted by Google somewhere in a lot of systems, distributed systems. Those are different levels of discussions. But what happens there is that the requests come from all over asking for a web pages. When a request comes in, the server checks to see if the page needs in whatever page you are referring to, if it is in the cache itself. So do you remember what is cache in the context of operating system? Anybody want to give me an idea about cache in your own word? It doesn't matter. All answers are good answers. No answer is bad answer.
Memory.
Exactly. I mean, some temporary memory. Uh, so cache is a temporary memory. So basically, uh, what happens when you run a web server and you request a website to the web server, it does not go to anywhere else first. So what happens? The model is pretty simple. I mean, let's try to draw something up. So in the operating system, the conceptual things, it is best represented if you draw the things up. So basically, this is a machine with this is a web server. So this web server has multiple things. I mean, we don't know what are things we have, but let's say we have a system that saves a lot of data in the web server. And then we have a cache system. So the concept is the external request comes into the system. It requests for a website, www dot whatever website, my website. I mean, it's an arbitrary website, fictional website, fictitious website.com. Then what it does, it looks for the website, whether this web page is somewhere in the cache area. Now, the advantage is then the cache is the temporary memory that is residing on the operating system itself. It does not have to go anywhere outside of it or anywhere in the depth of its hierarchy to find that resource. So if it will basically try to find the website into the cache, you know, if it is then if it is available, then it will show that page from the cache itself. If it is not available, then it requests for the disk. I mean, it will make a disk request to fetch that website. However, from the perspective of CPU, if you think about the CPU, the disk request may take a lot of time. While waiting for a disk request to complete, many more requests may come in, right? So if there are multiple disks present, some or all of the newer ones may be fired off to other disks long before the first request is satisfied. So clearly, some way is needed to model and control this concurrency. I mean, you can have lot of requests coming in to this web service at the same time. So how do you handle all these requests, all these concurrent, or concurrent means everything is happening at the same time. So the processes and the sub processes, or um, something called threads, can help us here. So we will we will discuss about it. Consider that you have a PC. When the system is booted, many processes are secretly started, often unknown to the user. The background processes, for example, that we just showed to you, those processes even do not know that a background process exists. When we start up our PC, we may have a PC started with just Chrome, but we do not know that there are hundreds or thousands of background processes running to maintain the PC, you know. So a processes, for example, that can start up to wait for incoming email. Another processes may run on behalf of the antivirus that we have uploaded to the system. I mean, to our computer. The other user level processes may be running as well, like file printing, the the backup process for users, photos. I mean, all those things are running, right? All these activities has to be managed, and a multi-programming system, multiple tasks, right? Yes, last day we talked about the multi-programming model, that is multiple tasks, multitasking kind of thing. Supporting multiple processes comes in very handy here. Even simple computing devices such as, let us say, smartphones, tablets, can support multiple processes. So in a multi-programming system, each CPU switches from process to process very quickly, running each of the tens or maybe thousands. Um, I mean, running each for tens or maybe hundreds of milliseconds. While strictly speaking, at any one instance, each CPU is running only one process. In the course of 1 second, it may work on several of them, giving the illusion of some kind of parallel processing. Some people may speak about parallelism in this context to contrast it with the true hardware parallel processes of the multiprocessor system. So when we talk about the multiprocessor system, remember there are multiple processors, everything is running parallelly. So in order to keep track of multiple parallel activities, I mean, it is very hard for us to do, right? I mean, you cannot do that by manually. So operating system designers over the years have evolved the conceptual model that makes parallelism quite easier to deal with. That model, its uses and some of its consequences form of the, that's what we are understanding here. So we are concerned here. I mean, we are basically focusing on the model of the processes. So we are talking about the processes. We are talking about the model for the processes. Um, in this model, actually, all software that is running on the computer, sometimes including the operating system, is organized into number of sequential processes or just processes. Let's say some processes, like I showed you, um, like you have the Chrome, we have the taskbar for the window. Each of those entries in the taskbar represent a process. So those are the processes running concurrently at the same time on your machine. So conceptually, each process has its own virtual CPU. Each process occupies some part of the CPU. In reality, each real CPU switches back and forth from one process to another process. The entire CPU of the system is shared among those processes. But to understand the system, it is much easier to think about a collection of processes running in parallel that can try to keep track of how each CPU switches from program to program. So basically you can think about this is this is your computer. There are multiple tasks. These are the dotted lines. These lines are the tasks, and then you have a CPU available to the computer, right? You can think about each of the process has a um, virtual CPU assigned to it. But I mean, from the hardware perspective, it's not possible, right? You have each process has its own CPU. It does not. But in order to understand the parallel processing scenario, what is happening, these processes are running and then it shares the same CPU one by one. I mean, maybe this amount of CPU can support these many processes. Let's say this. But then what happens to remaining two? Basically, for the remaining two, the CPU will be shared equally by some preferences among all the processes. So there will be a sequential transformation from one process to another process that we do not see in practice, but that happens actually behind the scene in the operating system, and that is something which is called our process model. So you see here, we have constructed a multi-programming model for 4 programs A, B, C, D. So you can see here. So we have, let's say, I mean, one program counter. You have one program counter. So this is different programs. So these arrows are the counters. They basically different processes are switched from one to another. The conceptual model for independent sequential processes that's as follows here. You see each process is running sequentially or maybe concurrently. But then you can see here in the third picture, at a given point of time, only one program is active. So let's say our time starts from here. So let me open up the pen. So let's say our time starts from here. So at this time, only this process A is running. After that, it switches to the process B. After that, it switches to process C. Then it switches to process D. Again, A, B, C, D. In this way, I mean, this sequence moves on with time periodically, but to the user's perception, we think that these processes are running, all processes are running at the same time, you know. But the process model is basically like that. I mean, one process is running, just one process is running at one time. This is the most like fundamental model of the processes. So this is a multi-programming model for the computer. So this is a very simple multi-programming model of a computer which contains 4 processes, you know, and then each one running independently of the other processes. Of course, there is only one physical program counter. So when each process runs, its logical program is, I mean, its logical program counter or the pointer to the program is loaded into the real program counter. When it is finished, the physical program counter is saved in the process stored in the logical program counter in memory. So we can see that over a long enough time interval, all the, I mean in the picture C, we see here that for a long time interval, all the processes have made progress, but any given instance, only one process is actually running. Not that all the processes are multiple at the same time, all the processes are running. Only one only one program is running at the same time. Okay, so that's pretty much the multi-programming model that we are talking about in this chapter. So this is the most simplest scenario of a multi-programming model. So let's move on. A process. I mean, let's move to more important aspects of the process. Now, before even we switch to the new slide, let's talk about. I mean, we will assume that there is only one CPU. You know, often that assumption does not hold true, since new chips are often multi-core with 2, 4, or more cores. We will look into multi-core chips. I mean, we will not talk about here. So basically, when we say that a CPU can really run only one process at a time, if there are two cores, each of them can run only one process at a time. With the CPU switching back and forth among multiple processes, the rate at which a process performs its computation will not be uniform and probably not even reproducible if the same process is run again. So the orchestration of this process is very arbitrary within the model, within this multi-programming model. But I mean, you don't have to go through a lot of theory. Just remember that. Just I mean, create a conceptual. Uh, create a concept about around the multi-programming, which is kind of multitasking. And here, for example, there are 4 tasks, but when in a real processor, real CPU, we have a program counter, means the program when the program runs, that counter is pointed to that particular program, and that makes the CPU acts like only one program on only one process can run at the same time at a given instance of time. But over a large amount of time, it seems to us that all processes are running concurrently. So the parallelism that is shown in the operating system, it is kind of virtual parallelism. In practice, what happens here, one process runs at a given instance of time without any interruption, and then that process stops. Then the second process triggers in. So that when that process stops, the first process stops, it saves its state. Then comes the second process, it runs, it saves its states, and so on. It goes on. And then when the process one comes back, then wherever it is saved, from there, the remaining tasks associated with the same process kicks in. So that's how the processes run within this multi-programming model. Now, we should understand as well the difference between a process and a program. So far we were talking that a process is just like a program, but we have to understand, are they same or not? The difference. An analogy. Let's get help of an example. Consider a like let's say someone is baking a birthday cake for someone. Now the person who is baking the birthday cake has a birthday cake recipe and a kitchen well stocked with all the inputs, flour, eggs, sugar, extract of vanilla, and so on. in this particular example, the recipe is the program. The recipe, the flour, eggs, sugar, extract of vanilla, and all the recipes. I mean, all the inputs, and then how do you mix up the inputs? That's the recipe. That's the program. That is an algorithm of making the cake. That is the program. Uh, the process is the activity consisting of the baking. The baker reads the recipe, fetching from the ingredients and baking the cake. The activity is the process, whereas the algorithm is the program. You understand the difference, right? The program is the algorithm, the 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 flow chart, the internal like understanding the building block of the process. The process is the activity. I mean, once it starts, then it goes through that algorithm. But the process is not the algorithm. Process is the activity, whereas program is the algorithm. So that's the difference between a process and a program. Now think about, I mean, that's pretty much. I mean, that's that's the uh, that's the process. I mean, that's the difference between the program and process. Now that let's say somebody else, I mean, whoever is baking the cake. Now within that room, somebody came and like somebody is asking him about something else. Like we do the multitasking. I'm baking the cake. All of a sudden, my friend comes in and they say that they have been, let's say, stung by a bee. I mean, whatever it is, something happened. So I mean, so what I do typically in that case, suppose I have to run to help my friend with his bee stung. So what I'm going to do, I'm going to record where I was in the recipe, the state of the current. So I save it. Then I get out, bring the first aid box, and then start following the directions in the first aid box to help my friend. And so basically, the processor inside me switch from baking of a cake to a higher priority process, that is some healthcare process. So each having a different program, right? I mean, the recipe in case the baking of the cake has a recipe uh, versus the healthcare programs and the first aid instructions. So when the medical situation is taken care of, I go back to my to the kitchen, and then I start continuing the baking of cake where I left off. So that's how basically the entire orchestration of the process in a computer uh, goes on. The key idea here is that a process is an activity of some kind. It has a program, input, output, and a state. Always remember the process has uh, four things: program, that is algorithm. It has the input, it has the output, and a state. A single processor may be shared among several processes, with some scheduling algorithm being accustomed to determine when to stop work on one process and serve a different process. But the program is something that may be stored on a disk, not doing anything. You can save a program on disk and just keep it there. It is worth nothing that if a program is running twice, it counts as two processes. If you run the two programs, one program twice, that means you are running two processes. You know, so that's pretty much the distinction between the program and the processes. Now let's give a break and let's come back at 7 p.m. And when we come back, we will, I mean, we studied up to this point, but then we will trigger into some hands-on exercise involving some Mint Linux. So be prepared for that. If possible, try to trigger your your system, I will ask one of you to share your screen, and we will practice together the I mean hands-on the Mint Linux commands, different I mean exercises on your system. So stay tuned for that, okay? We want to, I mean, we don't want to get bored with all the theories all the times. We want to do some mixture of theory plus some hands-on exercises, because in operating system in the computer science or the application development, the most important thing is hands-on, being hands-on. So that's what we are trying to be. Let's give a break and let's come back around 7 p.m. and we will catch up from there. Welcome back. Um, so, one, do any of you want to share your Mint Linux so that we can start working on one of the assignments that we will do today? Any volunteer?
Sure, I'll make mine come up real quick.
Okay, yeah, share your screen. We will go through the exercise. Very nice. Let
I
me,
guess that's
yeah, that's, what is that? Yeah, you can do the, what is happening here? Zoomed out. That's okay. I mean, we don't. So where is your remaining screen for for the Mint? There are,
I don't. It was
okay.
working fine, unless I just hit something just now and it made it this big.
Okay, so go to the terminal. So what happens here? Can you restart your Mint Linux again? I mean, it should be, there should be some. Uh, I missed that part actually. I was organizing my stuff. So close window. Yeah, that is the link Mint Linux, and you are opening the terminal, right? Open the terminal. Yeah, that is good. So let's keep it in that way. This is
Oh,
good. This looks good. So let's uh, let's go to the exercise that we can do today um, in this hour. So let me open up that exercise. That should be hands-on file system navigation in Linux Mint. That's the week 2 hands-on. I mean, the main benefit. I mean, I am encouraging everyone else to start their own Mint Linux, and we can complete this exercise as a whole. So uh, you have, so the only two requirements needs to be met. I mean, first of all, Mint needs to be installed in a virtual machine, and number two is the terminal or command line interface for well, I'm sorry, Mint Linux is available. So those are the two small requirements. I believe every one of us have this. So, so you open the terminal in the Linux Mint, and can you use the cd command to navigate to different folders? So if you do there, I mean, don't type cd yet. Can you do ls list? I mean, ls, just ls and enter. Okay, so ls command, this is basically used to list all the contents of the current directory. So do you know how do you determine what is your current directory, which folder you are in?
All the ones that are blue.
Yeah, but which one you are in? So basically you have to type pwd. That way you will know where you are right now. So enter. So you are in home. I mean your username here. If somebody else logs into the system, they will find their username. So we learn, I mean, basically what we see here is that when you log in into your Mint Linux, basically the first folder where you are in is your home directory. So that's how the operating system works. That's basic navigation in the operating system. I mean, the Linux operating system, the one we have installed here. So now we want to go to a different directory. So the first project is navigating the file system. So we opened the terminal and now can we navigate to, I mean, use the cd command to go to different folders are there. Let's go to the, let's say desktop folder. So you have to use cd space desktop. I mean, no, this is the lower case. You have to use the exact
Oh,
case. It is case sensitive. This is another, yeah, enter. So you are in the desktop. And if you want to go back to your original folder, you have to do cd space dot dot. Can you do that? Cd space dot dot. Enter. So you are in your previous folder again. Now I'm showing you a quick trick. I mean, do cd, just type cd and then space, start typing capitalize DESK and press your
where's my?
tab. See, so you
Oh,
got your,
cool.
so that is one of the utilities that Linux enjoy. I believe same utilities there in Windows as well. So I mean, but we are focusing on Linux. So that is how you can navigating to a different directory. Now enter and let's see what are the contents. So if you do ls, what do you see? Ls, there is nothing, right?
Oh, yeah, there's
So
nothing.
yes, okay. So what we learned here, how to navigate to a different directory and how to list whatever the content of the directory. So can you do a quick comment like can you write touch touch space readme. I mean I'm creating a file readme and then then enter. Okay, so what did you do? Touch command did not found.
Oh, touch.
Touch. Touch. Oh, okay. We did a different file. Yeah, that's fine. Okay. So now can you do ls? So you have a file now. So touch is a command that you can create an empty file. Now if you do ls space -l, let's see what we find. Okay, so what we see here is that more detailed information about your file. The first field, I mean, there is a dash RW, whatever it is, that represents the accessibility of the file, who has access to it. We will talk about it later. But then we have one, the number one suggests that there is only one file. No file is linked with this file. this particular file. We did not link it with anything. Then the third is basically the owner of the file. The fourth field is the same name as the owner. It's a group name. Which group it is in. By default, it is in the same group name as the username. The next field is a number, which is the number of bytes in it. Is it what is written there?
0.
0. Okay, no, it's not number of bytes. It's something else. We will talk about it later. Then you have the July 3. I mean the timestamp associated with the file. Actually, the 0 represents the number of bytes because it's an empty file. So yeah. So can you do a quick thing like can you type VI V for Victor VIS space readme, enter, enter, yes. Okay, so we have opened the file. Can you press I? Okay, and then can you write something like whatever you want, you can write. ABCD, whatever you want. Okay. Okay, that's good. So can you do escape? Can you press escape?
Escape makes
Escape
makes it,
on your screen's top left hand side. There's an escape button.
you mean on my laptop or on
On your laptop? Yes.
yeah, it won't let me escape.
Yeah, I mean, if you escape, you will still be on the screen, but you have to hit the escape. So once you escape, now do shift, right? Shift and colon at the same time. Shift and colon. Okay, no, not many times, just once. And then write W, small w, then small q. Right quit, enter.
Oh, okay.
Okay, so you saved the file. So now if you do ls minus l again, let's see what you find. See here, it is not the same as before. You see there are 29 bytes in the file instead of 0 bytes in the previous case. So that means you have included something in the file. So you wrote something. So that accounts for 29 bytes. So that's basically a very basic operation in Linux. You create an empty file. You know that the timestamp is 2109 when you created it. Then you edited the file, open the file basically using the VI editor. VI is the name of an editor. It's a kind of advanced editor in Linux. There are many other editors as well. We will talk about those later. But using the VI editor, we basically modified the file. Now, let's try some variation of the ls commands. So can you do ls minus hl, ls minus hl? Okay, enter. So, I mean, there is no big difference, but you will find the big difference if you have a bigger file. Uh, it just says there are 29 bytes in the file, but if you have kilobytes of data, gigabytes of data, you will see those in the human readable format if you do the HL. Now,
can I ask a question?
Yeah, sure, go ahead.
What is the total 4.0K?
Total what?
All right, here.
Oh, okay. Total 4K is basically about 4 kilobyte. I mean, it's saying that so there are total 4 kilobytes of data inside it. I mean that data does not necessarily it is not necessarily meaning that this is the content of the file, but it has everything. I mean like all the other resources as well. So ls minus hl if I do, and total, what does it mean? The total output command, uh, it basically says that total number of blocks, you know, what is the total number of blocks taken up by the file? Whatever files are there, there is only one file. This is the total number of blocks it represents, the data blocks. So that's our navigate. So we have learned how to navigate to a folder, how to create a new file, how to list that file. So that's pretty much we learned so far. Let's go to the next stage. So we have already done the touch for command. Uh, let us do the touch again. I mean touch read me again. Let's do touch read me again. Okay, now do ls minus l. Let's see what happens. So you can see that number of bytes remain the same, but you see the timestamp on the file is updated to current timestamp right now, whatever time it is. So one of the benefits of the touch command, as you can see here, one of the benefits is if you for some reason want to update the timestamp on a file, then you can use the touch command. So without changing any content of the file. Otherwise, I mean, if you want to use the vi command, for example, you have to make some changes in order to alter the timestamp. But touch command, by executing a touch command, you can update the timestamp on the file without doing anything else. I mean, without changing the file's content itself. So that is the way we can create a file, we can edit a file, we can update the timestamp of a file. Now let's move to a different command. Let's write mkdir, mkdir, and then space, and then create a new folder. I mean, like whatever folder name you want to do, test maybe, whatever you want. Okay, enter. So if you now do ls minus l, what do you see? So you see there are two different objects. One is the readme we created, that is a file, and there is a folder called test. The folder is distinguishable by the color code. And always remember that Linux is very case sensitive. So if you write capitalized T in the test, then all references you have to refer that. So can you do ls minus hl here? Minus hl, ls minus hl.
Oh,
Yeah. Okay. So here you can see again, I mean, this is the 4K. I mean, basically you have added a 4K block to it. So you have total 8K block in the folder and 4K in the new directory itself, the test directory itself. So we have learned how do you create a directory, mkdir command, and how do you basically create a new directory, and then we executed the ls command to list all the newly created folders as well as the existing folders as well. Uh, I'm giving you some bonus thing, like let us create a file touch. Let us write the command touch and then space and then do dot abc. Dot abc. Okay, enter. Now if you do ls minus l, let's see what are the contents. So you see that dot abc is not visible. So what does it mean? So basically what happens here is that in Linux, when you create a new file, starting with dot, that file is by construction invisible. You cannot view that file. So any dot extended files are invisible in Linux. So that is another thing. But then how can you view those files? The answer is if you do ls minus al, let's see what happens. ls minus al. Yeah, enter. So now you can see that there is the .abc, and so that a .abc file is visible by minus -al command. So basically a minus a option with Linux represents that you are displaying the hidden files as well. Any file that starts with dot is called a hidden file. Now you see here there are two other objects as well, basically two directories. First is dot, another is double dot. So what are those things? So whenever you are in a folder in Linux, you get two objects for free. Number one is dot. Dot represents the current folder.
Bag upstairs.
And then you have double dot that represents the folder.
Backpack. I only got one bag up there.
So a
It's
folder
in one.
that
It's in one of the box things.
so the second one, the double dot represents a folder. It is a little bit at the higher level. The next the previous level. So if you do cd double dot here, you will go to the desktop folder. I mean basically the folder. Yeah. So before desktop, the home directory. So that's pretty much the directory structure for the Linux. Now, while you are inside the desktop folder, you can navigate to test folder by doing a cd, right? I mean, let's go to desktop.
I'll go to desktop.
Desktop, yeah, cd desktop. You can do tab whenever you want.
Oh, thanks, Larry.
Oh,
Yeah.
okay.
Yeah,
And
that's all I
then,
needed. Thanks.
yeah, if you do, if you do cd and then do the test, cd and test, capitalize T, and then you can press tab. Okay, so then enter. So you are inside the test folder right now. It is empty, but you can go there by using that command. So, I mean, we learned more things than it is asking us to do. So basically we learned how to create a file using the touch command. Remember that if you want to create an empty file, you should be using the command touch touch. Then we learned about the mkdir command. That command is used to learn to make a directory. Mkdir, I mean, itself is make directory. I mean, that kind of thing. And then you do the ls command to verify what are the contents of the directory, the files and directory that we have created by using the ls command. Now, let's do another thing. I mean, let's go to, yeah, let's type cd double dots, yeah, enter. So we are in the desktop folder. Now, what we can do, can we type the command mv, m for move, mv, v for victory, space,
Oh,
oh,
sorry.
mv, yeah, that's okay.
Uh,
mv space, and then let's do readme, and then space, another space. Let's do readme2, readme, and then a word. Yeah, that's okay. Enter. So now let us do the ls. So what we find here that readme file is gone, but we have the readme2. So that's the implication of the move command. What you did here is that you moved the readme file to readme2 to a different name. What does it mean? Basically, what happens here is that you have readme file created that has a space in your memory. Now you moved the name, the representation of the file to readme2. That means your name has changed. The name of the file has been changed. Now, if you open readme2, let's see what is there. I mean, can you do, let's do, I mean, other than vi, let's learn a new command then. Let's write more, M-O-R-E, more, space, readme2. Yeah, enter. So you see that the content of the file remains the same. We have the same content. I want some chicken and soda, the one you wrote there, but the name of the file has changed. So this is called the moving. So when we move from one house to another house, our houses become different, but the people become the same. They are the same, right? Same people are moving from one house to another house. So same way, one file is moved from one name to another name, but the resident of the file, the basically the content of the file remains the same. So that's the move command. That's how you can move one folder to another folder. Now we will do another aspect of not moving but renaming things. Can you do like CP and space, and you can do readme2 and then space readme3. 3. Enter. Now let's do ls. So what do we find? You see that there are two folders, two files created, readme2 and readme3. Readme2 was already there, but we have copied the readme2 into another file called readme3. Now do more readme3. Let's see about the contents. So the contents are the same. So basically we have copied the readme2 file into readme3. So that's called the copy command. CP stands for copy. MV stands for move. When you move, basically you lose your current file name. It is as if like your current file is deleted and a new file with the same content is created. But when you do the copy, it means your current file remains in space as it is. I mean, it's just, I mean, a new file with a new name is created. So that's the difference between copy and move commands. So now let's do another round of command lines. Let's use the command rm. And can you do rm? Rm stands for remove. Readme3 and then enter and ls. So you see here that readme3 file is gone. So rm is the command which is basically removing the files. So now there is a difference between how the files are removed in Linux versus how the files are removed in Windows. When you remove a file or delete a file on your Windows machine, it goes to some space called recycle bin. But a word of caution, with Linux, it does not go to any such space. I mean, it does not go to the recycle bin. It is deleted permanently. So use absolute caution when you delete something in Linux because you may not be able to recover it. So only way to recover it if the system is backed up by some process, if there is a backup or something like that, which is unlikely on your personal machine. So that's, I mean, like from my experience, I can tell you, I have lost a lot of data. I mean, in that way, accidentally deleted a lot of things, but then could not recover those. So try to do some caution to delete the files. So if you do, for example, let's do touch readme 3. I mean, let's create an empty file and do the experiment. Readme 3. So you enter, uh, enter. So you have created the file readme 3. ls, do the ls, please. Okay. Now let's do rm minus I
Hmm?
minus I minus I mean dash I, rm dash I. No, not that, like that. rm, what are you typing? There's a dollar something. No, not si. I mean, can you remove the comment that you put there? Okay. Now put a dash I not e, I for ink. Yeah, and space readme 3.
Dimitri?
Readme 3. I mean the file that you created.
Oh,
Readme 3. Yeah. Okay, enter. So you see here that this is some kind of interactive delete. So it will ask you whether you should remove that file. So this is one of the ways. I mean, you can give your user a caution, uh, like should you delete the file? If you now do yes, then it will be deleted. If you write y, it will be deleted. If you write n, it will not be deleted. So if you write n, what happens? Let's just do n, enter. So now do the ls. So you see that the file is not deleted. So that means this depending on the reply to that comment, your file is deleted or not deleted. So the best practice, if you have really sensitive data somewhere, not sensitive, I mean important data to you somewhere, then use -i command for deleting it. There are ways to configure your system to do a rm-i when you called rm. We'll talk about that later. Now let's do one thing. I mean, we have a folder, right? Can you try rm test? Rm remove test. Capital T. It
oh,
starts with capital T. Yeah. Enter. So you see that you cannot remove test. It's a directory. So rm command does not work on a directory. Can you do? I mean, for deleting a directory, you have to use rmdir. So let's do rmdir and then space capital T tst. Yeah, enter. So ls, do an ls. So test folder is gone. Let's recreate the test folder. mkdir capital test, capitalized T. Yeah, that's fine. Small t is will work as well. Do cd test. No, cd space tst. Yeah. So now let us do touch ABC. I mean, I'm creating a file called ABC. So what does it mean that this test directory is not an empty directory anymore? So do cd dot dot. No, space dot dot. Yeah, enter. Now you have ls, do an ls. Ls. Yeah, that's good. Even better comment. Yeah, enter. So you have three different elements. Test folder is also there, but the test is not an empty directory, we know. So can you try rmdir test? Rmdir test. So you see here it is failing to delete because it's not an empty. So rmdir is a command to delete an empty directory. Now, in order to delete another, I mean, a non-empty directory, what you have to do, you have to write rm space minus r space minus r. So minus r is an option, recursive delete. So it will delete everything. So rm minus r space test. Enter. So ls, do that ls. So what happened here is that rm minus r command deleted the test directory as well as all the elements, all the directories, subdirectories, or files within the test directories. So that's why we use minus R option, which is called recursive delete. That means it goes into the file system and then recursively it deletes all the contents of that particular directory. So that's the importance of rm minus R command. So remember that if you want to delete an empty directory, you should be using rmdir command. Whereas if you want to use a non-empty directory, then you should use rm-r command. So that's basically the way you should handle the deletes. I mean, there are additional commands as well. So can you do go to do cd dot dot, I mean go to the upper level. Yes. Yeah. So you are deciding at the home directory. So can you write tree 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 yeah, enter. But um, the command tree is not found. Um, so probably did not uh, so can you do sudo apt install tree? I mean the one it says. We are learning this as well, how to install a command apt install tree. So these are the commands that system administrators use. So enter. So put your password. Okay. See, it is going through the installation process. Okay, now we are good. So now do the tree. Enter. Look. So your utility is installed. So you have learned how to install a command. That is the first thing you have learned here. And also as a second step, you have learned how, I mean, what is the result of this command? So what is this basically? It is uh, it will, I mean, the directories in the Linux operating system is like a tree structure. Tree means you have the main node. Under each node you have the branches. Under the branches you can have the leaves. That is the tree, right? So here you have the directory. Under the directory you have the subdirectory and so on. I mean, if you have, let us say, under the desktop, if you would have a test directory, then you'd see the test directory along with readme3, and underneath the test directory, if you have any other content like any file, then you would have seen in that with that tree structure. So tree represents the entire snapshot of the system. Since the file system in the Linux operating system is they follow the tree structure, so that's why it looks like that. And the tree structure is a basically from the data structure perspective, it is a most fundamental structure of I mean hierarchy, to put the data in a hierarchical way. Hierarchical way means you must have seen, I mean, like if you work somewhere or if you go through the genealogy, there is a hierarchy, right? I mean, you have the parent and then you have the child. In the work like organization structure, you will see the organization. Under the organization you have the child departments. Under the departments you will see the manager, the worker, all those things, all those objects, entities. So if you display the organization structure, you will see that in a tree structure way. I mean, in a tree, I mean, kind of level structures. So Linux file system also follows the same process. And I mean, Unix also have the tree structure for the file systems, kind of hierarchical structure. And using the command tree, you can find that, you can do that. So that's the tree command. Let's do a few more commands. Use the command find to search for files. So basically, can you write find and then space, do readme to enter. So no such file or directory because it is not within this particular file. Go to desktop, cd desktop. Yeah, now try to do find, not find readme 3. Enter. So you find this. Why do you use find? The main reason why we use find is that in a practical Linux folder, you can have thousands, tens of thousands of files you can have theoretically. So out of those tens of thousands of files, it is hard to navigate through each of them to identify, well, my file is there or not. So find is a quick command by which you can find any file. Now let's do some trick. Let's do find space readme star. Readme star. Yeah, enter. So you see that star is a wildcard character. So it means that whatever comes after readme will be displayed here. Uh, so if you do, for example, if you do find readme dot, let's see if you find something dot, enter. So there is no such file or directory. So star is sometimes they use dot to indicate one character, but it's not the case in this particular scenario. But remember that star is a wildcard. So it means any file name that starts with readme will be displayed using that particular pattern. It's kind of pattern recognition kind of thing. So if you have number of files, readme1, readme2, and then you have test, let us say, then only readme3 and readme2, those two files will be displayed. Test will not be displayed because test is not there before the wildcard character star. So star is kind of wildcard, and you will find all the similarly named files there. So that's the find command. Can you write a command du? Yeah, enter. So it means you are in the current folder. It shows you the space, basically how much disk has been used by this particular folder. Now if you do cd, let's do cd and enter. So you are going to the home directory. Now do the du, enter. So you see here that at the home directory, if you do the du, you will find lot of folders are there. And what are the disks occupied by all these folders? What is the disk space occupied by all these folders? So
Like
du,
4856A.
yes. So I mean, it represents all the folders that you have in your system and what are the disk usage by all those different folders. I mean, many of the folders you don't care about. I mean, those are the systems folder. Like we just talked in the first section of our lecture that an operating system can have a lot of background processes. So many of those folders represent the snapshot of the background processes that is running as a part of your Mint operating system itself. So That is the command. So now let's go back to your where I mean desktop, cd desktop, no, capitalize D.
So,
Yeah, always remember about case sensitivity when you do Linux. Yeah,
yeah,
enter.
keep forgetting.
Yeah. So now we are in Linux. Now we know that under the desktop we have readme 3 and readme 2. Let us do ln. Let us write ln space. Let us say ln desktop. I mean, sorry, readme 3, and space. Not readme 3, right? Readme 2, not 3. Let's no, not there. I mean, ln readme 2 and then space uh, xyz. Okay, so and do an ls now.
Oh.
Okay, so ls minus l, do an ls minus l. Okay, so it shows that you have an additional resource created called uh, xyz, but note that readme2, I mean there is a number before your username, that is a number 2. On xyz also there is a number 2 before your username. It means two files are linked together. So now if you do more xyz, what do you see? xyz. So you have the same content as the readme2. This is called hard linking of the file. So now if you delete readme2, let's see what happens.
Indeed.
Remove rm readme2. Okay, ls. So you still have xyz. If you do more xyz, so you have the content saved, but the linking is gone. The parent file is gone. So now if you do copy cp xyz space readme2, you are restoring the file basically, readme2. Okay, enter. So you have all the files. Now let's try another thing. ln minus s. No, I mean ln dash s, not minus. I'm sorry. ln space dash s, one s only. Yeah, space readme2 to space um, abc. Okay, enter. Now do ls minus l. We are doing another type of linking here. So you see here, ABC is linked to readme2, but this linking is called soft linking. It means that there is no new file created named ABC, but it is softly linked to the readme2 file. So now if you remove readme2, do rm readme2 and do the ls minus l. See, that is red, that means it is gone. So if you do more ABC, so there's nothing, I mean, it is gone. So the difference between ln and ln minus s is that ln represents the hard linking, where you have you create a persistent file, but ln minus s will create a soft linking, which is, I mean, it will be basically create a symbol in your file system, just a symbol. So it will be linked to the parent file. If the parent file is gone, your soft linked file is also gone. But your hard linked file will still be there. That's the difference between soft and hard linking. Now let's do another command, stat, S-T-A-T, stat, enter. So we have to put mm, some information, some commands. Let's see what are the options with the stat command example. I'm trying to find you some stat command. Let's do stat stat dash, I mean dash options, and then space, you can do readme 3. Okay, enter. Well, it's not options, so do the stat readme 3, only stat readme 3. Let's see what happens. Yeah, so basically it will show you the detailed statistics of that readme 3 file on the disk itself. I mean, it has zero size, zero block, I mean, all those are the zeros. There's access, I mean, whenever it was accessed, whenever it was last modified, whenever it is changed, whenever it was born, I mean, all those information are given there. So in the Linux system, if you want to analyze what happened to a particular file, you use the stat command. What happened last? What has happened last time with the file? That will reflect that stat command. So that basically it is for your first exercise for this week. So what I would do, I mean, you have completed it basically. So what you should do, you go back and whenever you create your Word document, just execute those statements on your assignment sequentially, and create a screenshot. That will give you full credit for this assignment. Okay, so let's give another break. I mean, 15 minutes break, and let's come back shortly after 8 p.m. and we will do a little bit of study, and then we will mix study and also the hands-on exercises. So do you think that you are getting enough information to be hands-on at the same time getting a little bit of theoretical perspective of whatever is happening?
Yes, sir.
Yeah, so I mean, don't stress yourself out with the terminologies. Don't don't be overwhelmed with the theory. Just remember the basic things. Just trying to create a picture and put the things in the picture whenever you go to the theory, because it's all abstracted. You don't need to remember all the terminologies. Just say, this is my process. This is the difference between a program and a process, things like that. Okay, we will come back soon. Let's stay tuned. Welcome back. So this hour, let's make a little bit of progress through our course. Then we will come back to the hands-ons. So basically, when we understand a process, you can there are three states of a process. I mean, we talked about process, right? I mean, it's like we have, I mean, processes are like the programs or applications, tasks, and an operating system accommodates multi-programming model, which is envisioned as multiple task, multitasking kind of thing. So each of the, I mean, each of the element in the multi-programming model is a process, right? The process can be in a running state, in a blocked state, or in a ready state. So basically what happens if it is in the blocked state, that means it is stalled, the execution is stalled. The ready state is basically it's not running, but it's not blocked anymore. I mean, if it gets sufficient trigger, it will start running. And the running is basically it is being executed. So the hierarchy is as follows. Uh, the process whenever it is blocked, I mean, number one, running to block, when it transferred from running to blocked, it blocks for input. Then number two is running to ready. It basically scheduler picks another process. Ready to running is scheduler picks this process, this particular process. So there is a scheduler that is supervising all the processes. It picks up a process or it can pick up another process. If it picks up another process, then this process is ready to be executed. Once the scheduler picks it up, it is running. And then number four, from block to ready, the input becomes available. So, so the difference between blocked and ready is the availability of the input. So when it is blocked, it cannot accept any input. When it is ready, then it is, I mean, inputs are available for those processes. Yeah, go ahead. Your question, Eric.
Yes, we cannot see your screen if you're demonstrating something.
Say that again. What's the problem?
If you have, if you're presenting something on the screen, we cannot see it. I know I
Oh,
can't see it.
you cannot see it. Okay, let me.
No.
Yeah, we're just seeing you.
Oh, okay. Let me try to do that. Are you able to see the screen now?
Yes.
Okay.
Thank you.
So let's repeat. Let's repeat the entire flow. So let's do a refresher. Like, you know, in the multi-programming model, everything is a process, right? I mean, we have multiple processes, multiple program, multiple process. We know that a program is kind of algorithm and process is the running state of the program. That's the distinction between a program and process. Program is a concept, process is the running, running state of that concept. And that concept is implemented by some technical infrastructure, maybe a Python program, maybe a whatever program language we can use. So it doesn't matter. I mean, we are not talking about programming language yet. We will do some programming, but that's a different aspect of this course. I mean, different exercise. In this week, we will do some programming. Anyways, so when a process, a particular program is running, I mean, it can have three different states: running, blocked, or ready. So running state is, I mean, basically when the process is transferred from running state to the blocked state, then basically the process uh, is blocked for input. No inputs are allowed to the process. So that is the definition of the blocked stage. Now, then from the running process to ready process means it is accepting the inputs, but the scheduler is not picking up that process. So in an operating system, we have the scheduler. The scheduler picks up given processes so that it can run. So, I mean, if you look at the task view of your window, it is something like that. I mean, you will see, just a second, um, task, no, not that one. Let me try to pull it up. Bear with me. So yeah, task manager. So what is happening here is that there is a scheduler somewhere. I mean, it is not visible here, but these apps are running. The scheduler is picking up each of the apps. So we don't see it quite, but what is happening, you see that there's a status. I mean, this status is different from the status that we were presenting here, because this is very, this status, this running block ready, these are very elementary status. So basically a process becomes blocked when it is blocked for input. No input can be given to the process. So the process is basically blind. It cannot see anything. So then it is blocked. But now the process can become, a running process can become ready if the scheduler does not pick it up. I mean, it may be so that scheduler picks up something else, some other process. Then this process becomes ready because it can accept the input, but it is not running. Now a blocked process is transformed into a ready process whenever it has the capability to accept the inputs. So what is the difference between a blocked one and a ready one? The blocked process cannot see any input. You cannot provide any input to a blocked process, but the ready process is ready for any inputs. It can accept the inputs, but the scheduler does not choose it to be running. So basically the difference between a ready and running process is that uh, fundamentally they are all ready for input, but running process is chosen by the selected by the uh, scheduler to run. So it is running, but the ready process is not selected by the scheduler at this time. So whenever it is selected, it will be transformed into the running stage. So that is all about the process states. So there are 4 principal events that cause a process to be created. First of all, the system initialization. So whenever you start up your Windows system, for example, then you will see that processes are created one by one. Sometimes you can do this experiment, like you start up your computer and then you initiate your taskbar. At that point, you will see that each of the processes are popping up one after another. Then there is another event that can cause the process to be created. That is the execution of a process creation system called by a running process. So a running process can it can make a system call where another process is created. Then a user may request to create a new process. I have nothing here. Now all of a sudden I'm deciding that I will create a uh, basically Microsoft Edge browser. I decided, so then this process is created. I mean, this is a new process that I have created. And then you can initiate a batch job. So you know what is a batch job? The batch job is basically some automated job. Um, for example, if you suppose you are in a school system, right? I mean, uh, you have a school software system when you are a student. What happened? One of the batch jobs in a traditional schooling system is statement generation. So each quarter, let us say, each quarter or each semester, each term, a job kicks into the system that creates the statements for the student. It can be the invoices, it can be the grade statement, whatever it is. I mean, that can be configured as a batch job. So whenever that batch job is triggered, then that process is created. I mean, the process of statement generation, whatever statement it is. We're not talking about very, I mean, like very lower level detail. We're talking about a process. Some process is created. So a process can be created in 4 ways. When the system starts up, initializes, or the process itself calls another process, or the user creates a request to run a process, or some batch job is running behind the scene. So there are only 4 ways you could create a process. So think about these steps in a very, I would say, very abstract way. Don't try to overthink about this. I mean, what is the process? What is the ingredient of the process? Let's consider some activity as a process. And then we will discuss about how the operating system is abstracting the things. So the concept, I mean, like we are the programmers. I mean, we are here for software development classes and we are the programmers. We have a tendency to think too much about anything associated with technical details. So whenever we see something, we sometimes we are diverted to think about, well, what is there in the program, what is the programming language they are using, what are the steps, and by thinking that we stress ourselves out. We should not be stressing out when we think about the operating system, because operating system is all about somebody else has written a program for you, right? Maintaining the program is not your problem, it's somebody else's problem. You are the user. You can be a system administrator, still you are a user because you are using the command line tools. Those tools, you are not creating those tools, somebody else created that tools. All you have to know how to use those tools. That's why we were having those command line sessions, installation sessions. So we have to know the abstraction level. So operating system is all about abstracting a system. So whenever we think about any details about the operating system, our thought process will always be conceptual, not very technical, very low level technical. So that's pretty much when we talk about the introduction to any operating system, we should think about in that direction. Now, next comes the process termination. So you can kill a process, right? So the killer process, it can happen a lot of ways. Number one is normally it is done. I mean, it completes the execution, it's done. Let's say you have a program, you have a batch process, your statement is generated, so it stops execution. That's a normal termination, normal exit. It can have the error exit as well. Let's say we we start up our PowerPoint. But then what happened? Something went wrong inside the PowerPoint. Some resources are not available. Then you can have an error. I mean, error exit. The process is errored out. You are not the one who is creating the error code, but the process itself. So you will see the error code and determine what to do next. I mean, like reinstall it, going to the experts about whatever is done, do the Googling. It includes everything. You talk to your co-workers. So that's up to you. So, I mean, there's the error exit. These are the voluntary normal exit, but it can have a fatal error. Like you are running something, all on a sudden it crashes. The system crashes, for example. This is involuntary and this can be dangerous. Fatal is dangerous. So, I mean, of course, you have to reach out to the experts in those cases, or your process can be killed by another process. Maybe you have a sequence of process, the and during that process, let's say you have the statement generation process running. Now you have a parent job which looks into some information in the system, and it found on the way that a student is no longer active in the system, yet that person's statement is still generated. So then what will happen, that parent process will kill that statement generation process for that particular student, because that person is no longer active within the system. um, Maybe that person passed, I mean they got the degree, they are doing something else not associated with the school anymore. So in that case, this is an example of the process killed by another process. So four ways to terminate the process: normal exit, error exit, fatal error, and killed by another process. So the first two are the voluntary termination. Number two, last two are the involuntary. I mean, the process does not wish to be killed or terminated, but the situation, the system killed it. So this is the process termination. So we have learned about process creation and process termination. Then the lowest layer of a process structured operating system handles the interrupts and scheduling. I mean, so basically you have the scheduler. We were talking about the scheduler, right? I mean, it is the parent system, some monitoring system that will do all the scheduling process in an operating system. You have some scheduler. So what it does, I mean, it has operating system has 0 to, I mean, n number of processes, and the scheduler comes here, and it can schedule the processes sequentially. It will monitor the process, and it will, and there is a whole lot of internal process going on. Like there are monitoring system that will see whether a process is done, and when process 0 is done, the scheduler will know that process 0 is done, then it will schedule process 1. I mean, things work in that way. It's like a normal scheduler. I mean, I mean, the person who is scheduling certain things, so that person will know, right? I mean, the task 1 is done, so that person will schedule the task 2, I mean, in this way. So think about it in this manner. So the processes are stored in a table in an operating system. Table is like a file, you know. There is no difference between a file and a table. So basically you include the information in a file, but that file is structured file. I mean, it's not an ad hoc, openly written file, a very free written information. It's not like that. It's structured. So some of the fields, the file contains the fields, and the process table has following fields. Like it has fields related to the process management, it has fields related to the memory management, it has field related to the file management. Because you have the process, you have the memory, you have the files. I mean, three important ingredients of the operating system. The files are the one which stores information long time, I mean persistent storage. The memory is temporary storage. I mean, I mean, it manages the processes. It gives processes the memory so that it can execute the tasks. And the process management itself is a complicated thing. I mean, it contains the registers, program counter, the program that, I mean, there is a counter that knows that program number 1 is running versus program number 10 is running. Then it has the status word and the status of the process, the state, the priority. I mean, you are running a process, you know, on a operating system, but is it a priority process? If not, then it can go to the lower priority. The operating system has its own way to set up the priority. Then the parent process, the process group. I mean, all those things, they fall under the process management. So, but all you have to remember that there are three categories of fields: process management, memory management, and file management. The files are the persistent storage. Memory is used for running the process. It gives you capability, the operating system capability to run a program. And then the process management itself is a, I mean, I mean, basically, how do you manage one process and after another process? How do you management the individual process itself? So that is related to the process management, and it has several fields to consider. So that's pretty much the process table entry. Any questions? I mean, you can always interrupt me to ask the questions if you have any, and if you have questions later on, you are free to ask me. You can text me. Some of you have been texting me regarding a lot of issues, and I've been trying to fast enough to reply those. Uh, so just do reach out to me if you have any questions. Now, the skeleton of what the lowest level of the operating system does when an interrupt occurs. So interrupt is basically something is going on. Interrupt is literally grammatical meaning, like something is going on and you are disturbing to get it changed. So initiation of some changes. The details, I mean, details of that may vary between different flavors of the operating systems. So, I mean, the, the when the interrupt occurs, I mean, the hardware stack program counter, the hardware loads new, I mean, basically the hardware that can stacks the program counter. Hardware can load new program counter from the interrupt vector. Interrupt vector is basically the interruption, the command, series of commands, interrupt commands. Then you can have the assembly language procedure saves the registers. I mean, a lot of steps are there. It's not super important to memorize all the steps, but do understand that, I mean, in an operating system, when it's a coordinated execution of different processes. So interrupts are the ways for the change. If you want to change something in the operating system, or the operating system itself wants to change something, something is automated, it will cause an interruption in the system. Then it will do a lot of different, it will execute a lot of low level processes, and some of those are written here. Like, I mean, hardware stacks program, hardware loads new program, assembly language processes saves the registers, assembly language procedure sets up new stack. I mean, all those things. Scheduler decides which process to run next. So whenever there is some interruption, it will basically initiate a series of courses of action. Some of those are written here, but interrupts are the means to change something in the operating system, you know. So that's basically basic refresher about it. Now, CPU, I mean, the operating system also keeps track of the processes, and the processes are controlled. Sometimes it is controlled the by how much CPU is utilized. So we are always remember, when we talk about operating system, we are talking about multi-programming. That is the basic, absolute basic concept. You know, when you run a program by yourself, you are doing single programming. Like you are running a Python code, you are running a C code, you are running a Java code. That's a single program. Or you are running a web server, that is also a single program. But whenever you are running an operating system, whenever you are in an operating system, the concept is always multitasking or multi-programming. So the multi-programming has its own challenges. So you have the CPUs everywhere. I mean, CPU is always costly. So uh, if you have the degree of multi-programming, you can think about degree of multi-programming is how many concurrent programs are running. I mean, it's not really like that, but it may be like that, thought of like that. So when you talk about operating system, we should always think about abstracted concepts. So like the degree of multi-programming, how many programs are running, and then what is the usage of the CPUs. So you can see that uh, we have three different behaviors. The red one, it says 80% of input output is wasted in waiting for different processes. The green one shows the 50% of the input output is basically waiting for the availability of the processes. But the blue one is the most efficient one. It says 20% of the input output wait. So the approach to the operating system should always to minimize the wait, because whatever you are waiting, that is a wastage, true wastage in a job execution system in your workplace. If you have some infrastructure that you have to wait for something, some work, um, something, so you have to wait for decisions to be made, you have to wait for somebody else does their job, then that infrastructure is not very efficient. If you have an infrastructure where your waiting time is minimized, that means you are utilizing your system. So here the CPU utilization and degree of multiprogramming. So if your wait input output wait is minimized, so then you can say that your CPU utilization is optimized if your waiting time is minimized. So that's what is happening in the green, in the blue plot. The red plot is not acceptable. The green plot is, I mean, somehow it is in between, but the blue plot is the ideal. I mean, you have the minimum input output wait. So uh, that's the basic concept of the CPU utilization as a sorry, what I'm doing. I switched to a different tab. Okay, that's fine. So as a function of the CPU utilization. So that's pretty much the implication of the card that we talked about. Okay. So so basically here, I mean, again, I mean, reiterating. So you, in this case, the red plot, I'm trying to interpret it in multiple different ways. So you can see here the red curve, it represents that the processes spend 80% of their time waiting for input and output. Okay. Um, so, I mean, so whenever you have that scenario, that is not a very ideal scenario. That's what I mean, we would say. So let's move on. So now we are talking about some examples of the processes. Um, so here uh, we are talking about the threads now. Uh, so we have the process as a program. Now we are introducing a newer concept called threads. So in a traditional operating system, each process has an address space and a single thread of control, single threaded program. For example, if you run your Python program, I don't know what level of programming you have learned so far. Let's say, I mean, any programming language, it can be Python, it can be JavaScript, whatever it is, HTML. So sometimes you run the program, most of the times, whenever you do the hello world, the process, each process, it has a single thread, you know, it's single thread of execution. We will discuss about threads, don't worry about it, but each process has a address space, it has the address, it has a, a place in the memory and a single thread of control. That is almost the definition of a process. In many situations, it can be useful to have different threads of control in the same address space running in a parallel mode. Give you an example. Okay, we were talking about the statement generation process. So there is a school. I'm trying to give example which is relevant in our environment, the present study environment. So you have a school, you have, let's say, 5,000 students in the school. It's a big school, let's say, and then the central, I mean, the software of the school, the system of the school, it runs the statement generation process. So it can run it in a different way, in many different ways. It can create one process as one statement, like you have a program and the same program is called 5,000 times. You can do that. But you can also do in this way, you can run this program, but all the 5,000 students statement is generated sequentially. So the question is, the first two models, are they efficient? Because in the first case, you have the 5,000 statement generation jobs. So they will struggle with each other for the memory. Then the second example, you have only one job, but then this is sequential. So that means by the time you complete, let us say you have to generate statement within 24 hours, it may be so that there are multiple activities involved. So you are not able to complete your tasks within 24 hours. I mean, that statement generation for all 5,000 students. Maybe there is a school with 50,000 students, maybe. So then the statement generation is even more challenging if you do that in sequential model. So how do you solve that problem? So that's our point right now. Um, so why would anyone want to have a kind of process? So we have a process running, statement generation. So we want to have a process inside a process. So what is that? There are several reasons of getting these mini processes. Like, for example, think about this model. You start the program for statement generation, and then you create some mini processes, each for one student within this master process. What is the advantage? Advantage is that if you are able to distribute these mini processes across different systems, across different memory spaces, then they will not interact with each other, and but they will be processed in a smooth manner. So this type of branching out the processes, creating the mini processes within the process, this is called threading. These mini processes are called the threads. So the many reasons, there are many reasons. One of the reasons I told you to get the parallelism in the statement generation example. The main reason of having threads is that many applications, multiple activities are going on at once at the same time. Similar type of activity, but multiple of them are going on. Some of this may block from time to time. By decomposing such an application into multiple sequential threads that run in a parallel mode, in that particular programming model is called the thread. For example, here you have the word processor. What is happening here? You see, you have the kernel. I mean, the kernel is the basically the heart of the operating system. You have the keyboard, you have the disk. I mean, all these three things are managed. I mean, you need to keep track of all these three processes when you run a word processor. So uh, you can do it in three different process, but then what happens when you do the keyboard, other two things are become they will stop. We don't want that. We want all three to work together. So that's why we create a word processor as a parent process. Under this process we have three mini processes: keyboard processing, the disk processing, and if there is any other, I mean the word processing, let us say. So that three sub-processes create a master process. So these three sub-processes are called the threads within this master process. Now, um, why we have the thread? I mean, we can think like, um, I mean, the second argument for having a thread is that since they are lighter weight than the process, I mean, each thread, I mean, it's a mini process, it has lightweight in terms of memory. Uh, so they are faster, they're easier and faster to be created and to be destroyed. In many systems, creating a thread goes 10 to 100 times faster than creating a process. When a number of threads needed changes dynamically and rapidly, this property is useful to have. I mean, uh, so basically the threads are, I mean, mini processes. Sometimes you don't need them, then you don't create them. But if there are processes defined, you have to create them no matter if you need them or not need them, they will be there. So they will charge some overhead all the time, the memory overhead. So threads are very lightweight and easy to use. The third reason for having a thread is also to from the performance argument. I mean, threads yield no performance gain when all of them are CPU bound, but when there is a substantial computing and also substantial input output, having threads allow these activities to overlap, the speeding up the application. So there are three different reasons of having the thread. Number one is basically to divide the process into the sub processes to avoid the overall memory usage, huge memory usage. Number two is that they are lighter and easier to execute the threads. And number three is that, uh, I mean, they accomplish parallel execution. So that improves the performance. I mean, threads are useful on systems with multiple CPUs where real parallelism is possible. If you have a single CPU, then your threads are not as effective. But if you have multiple CPUs in a system, then thread is really important. Like example, giving you an example, the statement generation process. Now you have a system. Um, Suppose you are putting that process into the AWS cloud. The cloud, what happens there is that there is a orchestrated parallelism using multiple nodes out there. Like nodes are machines. So you're distributing the same workload over the multiple nodes. So then if you have the multi-threaded application, the threads can be processed in different nodes. And then real benefits of executing the program parallelly is can be done. But if you have a single machine, single CPU, then you won't realize that benefit as much because the single machine is divided among different threads. So overall, the time consuming consumption will be the same no matter how you are using it. So for the multiple nodes, multiple CPUs, the threading model is very efficient. Now it is easiest to see why threads are useful by looking at some concrete examples. We were giving examples. Like here, what processor example, it usually display the document being created on the screen formatted exactly as will appear on the printed page. In particular, all the line breaks and page breaks are in their correct and final positions so that the user can inspect them and change the document if needed. Now, suppose that user is writing a book. From the author's point of view, it is easiest to keep the entire book as a single file to make it easier to search for topics, perform global substitutions, so on. But each chapter might be separate file as well. However, having every section and subsection as separate files is a real problem, you know. So, I mean, you can do like it has a lot of problems. Like suppose there is a standard imposed on the across the book. If the proposed standard is approved just before the book goes on press, it occurs that the draft standard have to be changed to some other standard at the last moment. The entire book is one file. Typically, a single command can do all the substitution. Suppose there is a typo, uh, consistent typo across the book. So your single command can do all substitution. But if you have multiple chapters divided into different files, then you have to do that number of substitutions. So consider what happened when the user suddenly deletes one sentence from the page one of an 800 page book. After checking the changed page for correctness, now the author wants to make another change on page number 600 and types in a command telling the word processor to go to that page, the word processor is now forced to reformat the entire book up to 600 because they have changed something in the first page that caused all the sequential lines to be changed across the book. So then if they search now, the book has to be reformatted. So that is a very slow process and may not be very good process. Now threads can help here. Suppose that the word processor is written as a two-threaded program. One thread interacts with the user, other handles reformatting in the background. As soon as the sentence is deleted from page one, the interactive thread tells the reformatting thread to reformat the whole book. Meanwhile, the interactive thread continues to listen to the keyboard and mouse and respond to the simple comments like the scrolling page one while the other thread is completing in the background. So having multiple thread eases the task of the program itself, you know. So that's basically the reason why we want to have the threaded program. So we understood that we need to have the processes to be more efficient. Threads are meant for adding more efficiency, easiness of execution. These are lightweight, so consume less memory, and these obtains parallelism. So the each job is executed faster if you use the threads. But one word of caution, if you have multiple CPU, then only the threading model is very useful. Otherwise, it is not that useful, you know. So that's pretty much our threaded model. So let's see, I mean, multi-threaded web server. So there is another example of I mean, web server. So basically what happens, you know, um, let's think about the web server, I mean the interactive programs. uh, so what happened here is that the server is to serve a website, right? Now it requests for pages to come in, and requested page is sent back to the client. You are doing the Google, you are requesting some page, then your server basically serves the page to the client. At the most websites, some pages are more commonly accessed than other pages. For example, if you go to, I mean, go to any web homepage of any company, this is accessed far more than a page deep in the hierarchy. Let's say if you go to CIAD, I mean your Canvas page, the course page is accessed more frequently than your files page, for example. So you have this, I mean, system stores all this information. The web server used this fact to improve the performance by maintaining a collection of heavily used pages in the main memory to eliminate the need to go to the disk to get them. Such a collection is called the cache and is used many other contexts as well. One of the ways to organize the web server is shown here in this picture. Actually, we are going to discuss it. Here, one thread, the dispatcher, you know, there is a dispatcher thread, one thread. The dispatcher thread reads incoming request for work from the network. After examining the request, it chooses an idle, I mean the block worker thread, this one, the worker thread. Let me bring the pen so that you know what I'm pointing to. Otherwise, if I just say the words, it will be confusing. So you can go to the worker thread and hands it the request, possibly by writing a pointer to the message into a special word associated with each thread. The dispatcher thread then wakes up. Um, I mean, the sleeping worker wakes up the sleeping worker and moving it from the blocked state to the ready state. So basically, that's pretty much the way it works. So when the worker wakes up, it checks to see if the request can be satisfied from the web page's cache. to which all threads have access. If not, it starts a read operation to get the page from the disk and blocks until the disk operation is completed. This is a very long process compared to the threaded process. When the thread blocks on the disk operation, another thread is chosen to run, possibly the dispatcher, in order to acquire more work, more requests, or possibly another worker that is now ready to run. This model, basically, overall this model, where you have the dispatcher thread, the worker thread, I mean, it is divided, the work is divided, then you have this model allows the server to be written as a collection of sequential threads. The dispatcher program consists of an infinite loop for getting work request and handing it off to the worker. Each worker code consists of an infinite loop consists of accepting a request from the dispatcher and checking the web cache to see if the page is present. Now, if so, it is returned to the client and the worker blocks waiting for a new request. If not, then it gets to the page from the disk, returns it to the client, and blocks waiting for a new request. A rough outline of the code. I mean, we can. Sorry, I have to do that. Okay. So basically, a rough outline of the code is given here. So while true, it means, I mean, while it is true that the situation is true, you get the next request. So basically this is the dispatcher thread, it's an infinite loop, and you have the worker thread. This is also an infinite loop. So it basically processes each request. It takes the request, it processes the request. So entire thing is divided into two main threads, dispatcher thread and the the worker thread. So the benefit, what is the benefit? If we do not have those threaded application, then single thread would do everything. And so it will wait until that is done. So here we are accepting multiple requests at the same time, and then the requests are disposed in this way in the thread B. So we are dividing each process into two lightweight processes. So we are threading these two processes. The main advantage of threading is that it is still part of the same process. If we initiate two different processes, then you have to explore some mechanism to transfer the data from process 1 to process 2. But since it is owned by a single process, you don't have to do it. The threads know about the data, common data in the program. So that's a benefit of running this thread. Now, consider how the web server could be written in an absence of thread. I mean, that's what we were discussing. I mean, everything should be a single process, and that will be very disturbing. So now, I mean, we have seen why the threads are very useful. We are trying to understand the thread model basically. The process model is based on two independent concepts: the processes, the resource grouping of the resources, and executing those resources. Sometimes it is useful to separate them. This is where the threads coming in. I mean, the classical thread model. We will look at the very preliminary thread model. One way of looking at the process is that it is convenient way to group together related resources. So you have the process in this picture. You have three processes, and with one thread. I mean, each process is a thread here. But in the second picture, you have a single process with multiple threads. So there are two different models of executing the tasks in the operating system. Here you have more processes. So what happens? You have to dedicate more memory. But here you have only one process. So you are assigning memory just once. But then the sub process is consuming this assigned memory. Uh, it is sharing the assigned memory and get the same job done in a much faster way. So that is the most preliminary thread model that we are discussing here. Now, the first column in this table list some of the items shared by all threads in a process. So let's say, I mean, that's the advantage of having the threads. As I said, the information, the resources, then do not need to be transmitted from one process to another process. Something that the threads share, that is the per process items, the address space, the threads, all the threads belong to the same address space, the global variables, open files, child processes, the alarms, signals, accounting information. But there are per thread items as well. Those are the program counter, registers, stack, and state. So thread has its own ecosystem. So we don't care about that ecosystem when we think, when we look at the process. We are basically, what is happening here is that your manager gets a project and assign the multiple, divide it into multiple parallelly executable tasks, and that person designates those tasks to multiple workers. He or she doesn't care about how you are doing those things. I mean, those are the per thread item, per worker items here on the right hand side. But your manager knows about what is the global scope of the work, that is the address space. I mean, the global variables, the deliverables. I mean, all those global things. That's what we care about. We don't care about what happens to the stack, what happens to the state of the threads. Ultimately, the threads needs to be completed, and that will give you some output. So that's the purpose of the multi-threading after all. So that's the very elementary model of the thread. So each thread has its own stack. So own stack means own memory space. Each stack thread has, it maintains its own stack. So it has, I mean, these stacks are independent. Thread one stack, this one, this guy. Um, Let me bring the pen up. So this stack is not visible by this thread, this stack, and this is not visible by this stack as well. They are independent of each other. So that's the beauty, because you don't interfere with whatever each thread is doing. If it were a process, then there will be a single stack and it will be shared among multiple processes, multiple sub processes. So in the threaded model, you have stacks. Stack is kind of memory space. You store all the essential information and you don't interfere. It does not have any interference from any other processes or threads, whatever it is. So that's the benefit of the stack for the threads. Now, some of the thread functions called pthreads is a way, is a function that calls the threads. I mean, basically you have pthread create, exit, join, yield. I mean, all the different function calls. Create is the new, creating a new thread. Exit is terminating a thread. Join is wait for a specific thread to exit. Yield is release the CPU to let another thread run. This one create an initialize threads attribute structure. Destroys basically threads attributes, remove a threads attribute structure. We'll talk about it during the example. Don't worry about the. So we will. This is the C program. Let's not jump into the complicated coding scenario. Let's give a break and let's come back and we will do some concluding discussions for today, and then we will wrap up and wait for the next session, which will happen on Wednesday. But let's come back after the break. We will talk more. Welcome back. Let's go through some quick discussions about our next assignment. I mean, I do not want to burden you with all the theoretical discussion at this hour. So just let's go through some interesting features. This is related to the chapter 2. The process is related, hands-on. So I'm entering into my Mint Linux system. Let me do a terminal. Yeah, here it is. So hopefully it is visible to you. Let me split the screens equally. Okay, so just a second. Let me just a second. Okay. So we have the basic. How do you know the processes in a Linux system? That's the question. So there are two commands that we have available for monitoring the processes. So let's do a, I mean, that's a PS, okay, process statistics kind of. So let's see.
Can anybody else hear? Because I can't hear nothing.
Bill thought it was just me. All right, thanks, fella. Hey, sir, we can't hear you.
Can you hear me now?
Yes, sir, you're back online.
Oh, yeah.
Okay, so my microphone was kind of, it became weird. Okay, thank you for confirming. Okay, so we are talking about the PS, that is the process statistics, I mean, snapshot of the current process. Here we have different versions of the PS commands. I mean, many of the PS commands you will see when you execute yourself, you will find that they are basically the same. This page is the man page for the PS command. For each command, you can do man and then the command name. You will see the information. So you can see here, there are three different versions of PS commands. One is the Unix option, another is the BSD. BSD is related to Berkeley software distribution. It's the same thing as Unix, but from different organization it initiated. The GNU long options are also there. Okay, so then there are options for different types. I mean, let's focus on PSAUX type of command. This required that this command, PSAUX, print all processes owned by a user named X, as well as printing all processes that would be selected by -A option. I mean, X is here, it means all users. X stands for all. If the user named X does not exist, the PS may interpret the command as PSAUX instead and print a warning. this behavior. Anyway, I mean, let's not go through the manual page, but basically you can have that ps aux command, and there can be different flavors of the ps command as well. The ps minus e, ps minus ef, so different things, and also you have like a PSAXU, that is same as PSAUX. But basically what it does, I mean, there are many more. Let's not jump into the command terminologies, but basically what it does, the PS command, what it reflects is basically, I mean, there are fundamental difference between PSX and PS AUX command. Let us So what I'm doing right now is doing some research here. I'm showing you, I mean, whenever you are in doubt, do the same thing. PSAUX versus PSEF. These are the commands we were asked in the exercise to explore. So what is the difference between these two? I mean, basically there are no difference in the output because the meanings are the same. The difference between PS minus EF and PSAUX is due to historical difference between POSIX and BSD system. At the beginning, POSIX accepted the minus EF, while BSD accepted only AUX command. So they basically do the same thing. So in the Ubuntu forum, Ubuntu is a flavor of Linux system. So this is a very authentic website. Uh, so in this forum, they say that both lists all processes of all users in all aspects. Minus E and AX are completely equivalent. Where they differ is output specifier minus F is the full, while U is the user oriented. So let's do the listing. So let's do PS minus EF. So you will see that, I mean, there are a lot of processes listed under there. So these are all running process, you know, by the system. And also if you do PS AUX, you will see the similar list. So basically the similar list, but I mean, different flavors of different systems. So you see that user level processes are here, as well as system level processes are here. I mean, used by different users, root versus my username. So those are the different. So let's go to the exercise, what it asks us to do. Where is that? Here. So what we can do here, run the command ps minus ef, then pipe more. That means you are basically paginating. I mean, if you do ps minus ef, it will print everything at once. So if we do like this, ps aux or ps minus ef, let us say ef pipe more, then you will do it interactively, page by page. So you can type this one and see, and we have to inspect what is going on here. So it displays a list of all currently executing processes running on the system in a scrollable format. So take a screenshot of that. I mean, you need to take a screenshot, then scroll through the list and identify the processes that were started when the system was booted. This process will typically have a 0 in the PPID column. So this is the PPID column. So you see here, everything that starts with 0, these processes have started when the system was booted in the first time. But then non-zero processes were, they took place afterwards. So here has been initialization, or I think this is kernel thread, whatever it is. I mean, that started when it got booted. So if you go to the subsequent part, you won't see any processes that started after it booted. So basically first two processes in our case, in my case specifically, they are the they have started when the system got booted. So that's how, looking at the PPID column, you will identify which processes started when the system booted versus which processes started afterwards. Okay, so that's the basic idea behind the ps minus ef command. Now so you can take the screenshots for the both, like take a screenshot for this one, uh, pointing that PPID process. These are the processes they were started when the system got booted. But then you can mention about some other non-zero processes. These are afterwards. These kicked in afterwards. So this is another thing. Uh, so then run the command ps minus ef mode to display a list of processes currently running on the system scrollable format. So basically you can do the same thing. Did we do that one? Yeah, we did that one, but you can do ps aux as well. I mean, these are, this is a different thing than the one we talked about. So you can do ps minus ef, this one. You have PID, PPID. That column is there for ps minus ef. But then you can do scroll. You can scroll through the needs list and take note of the user, command, CPU, and memory columns in each process. So you see here, CMD is here. The user ID is here. Where is the memory? Let's see. So let's do it again. PS minus EF. So you have the command, you have the UID. There is no memory thing here. But if you do PS minus PSAUX, then you should be able to see the CPU, the memory, the user, all these things here. So there is a variation between PS minus EF versus PS minus PSAUX command. So the task is to identify those things. Um, so basically for number 2, you should do PSAUX command, as I said here in this way, enter, and you will see the user, the root user. So it is not using any memory. CPU, it is using very nominal memory. But if you scroll down further, you will see like this one using some CPU as well as some memory. So those are the important fields that you can talk about. Just do a discussion around those. Just uh, take a screenshot in your screen and say that, see here, this particular process is using 0.3% of CPU and 10% of the memory. Just mention something like that. So that one, to store detail of all processes owned by the root in a file called root processes -1, uh, and all processes owned by you in a file called my processes -1. You can use that. Run the command ps minus ef. Then you do execute this command. Let's do that. So sorry, no, not that's not right. So paste. Oh, it's not possible. So let's do ps minus ef grep root processes, that one, ps minus ef. Then you do a pipe root. So you do grep root. We will discuss about what is grep, but right now just use this command root, and then we have root processes 1 greater than root processes 1. So if you do that, and then if you do more root processes 1, you will see all the root processes. So that's one flavor. So basically what it does, this command, so ps minus ef is the main command that you are executing. Then you do the pipe. That means you are putting some filter. Pipe, that symbol pipe, this one is used to designate some filter. Then you do, what is the filter? The grep is basically to find some pattern. So in this particular lookup, I mean, whatever text it is generating, you are trying to find the word root here, the root. Then you redirect, greater than stands for the redirecting these filters result into this file. So this is the way you can list, you can execute a command. Then you do a pipe, that is you are filtering. And then what you are filtering? You are using the grep command. So basically you are finding some structure, cultivate, doing some pattern matching. Then grep, then your pattern is root. So you are finding the word root in the file, and whatever has containing the root, you are redirecting it to the process, this file. So that's the essence of this particular uh, command. You can similarly do the other command as well, your username, and then you can do the my processes one. So in my case, my username is Deb, so I can do Deb, and then you can do, I can do my processes one. So if I do now my processes, sorry, more my processes one, you can see my username, but I don't know why it comes here Deb. So because it is, there is a match here. So I mean, there will be that, I mean, whenever you create the screenshot, you make a comment that it is owned by root, but I get my username because of this pattern matching. Maybe for your username, you won't get any pattern matching. For my username, I mean, there are a lot of matching occurring. So it depends from case to case. So to compare the files, this one and that one, I mean, the root process two, what is root process two? So root process one is there. What is root process two, by the way? Root process two, root processes two. Oh, here. Um, restart your system. Then you need to restart your machine and create similar files, this one and that one. I mean, this is during the first execution. Then what you should do, you should go to the virtual box. Basically, you can make it, I mean, stop, and then you power up. Then you do another screenshot, the same two screenshots again, and do some comparisons between the root processes that you have saved. So um, once you do that, you should be able to say, I mean, you should do the restart the system. After the system has booted up, means switch off and then you reboot the system. Run the same commands used earlier to store the, I mean, all these things. Run the command diff root process and this one. So let's do that. Why don't we do that? So let's do the stop and then power off. Power off. So we have powered it off. Now let's start it up again. I'm starting up the power, double clicking it, starting it up. I mean, let it come up. So it's starting up. There will be a music before it starts up. That's Mint music, basically. So I'm waiting for it. It's coming up. See, the cursor has showed up. Yeah, something is happening. So let it come. I still don't have any existence of mouse inside this box. Yeah, here it goes. Now the mouse cursor has showed up. So let me do test 1, 2, 3, 4. Now it will log into, I mean, Okay, now it comes up. So do it again. Yeah, here it goes. So now what we can do is that, I mean, let's create like PS minus EF, then do the pipe filter basically. Grep root. So what is the name? What is the naming convention? It's a root processes 2. So we created that. Now we have root processes 1 and root processes 2. Let's do a difference. Diff root processes 1, root processes 2. So if you do that, you will see a lot of differences between these two. So how do you look at differences? This less than sign shows the first file, this one. But if you look at greater than sign in the same file, that reflects the occurrences in the root processes too. So there is a lot of difference between these two files. Of course, I mean the timings should be different, the performance should be different, the PPID numbers can be different, and so on. So you can just create that diff, I mean the diff comment and then reflect on that. Just there is a lot of difference, and these are some examples, 2 examples of differences you can mention. So same thing for the my process, your user process, and that's it. I mean that's pretty much your second assignment. So it's also a not very hard piece of cake kind of. You can go through the process and do that. But then you will have the threaded process. So we will talk about it during our next session. These all coding stuff. I mean, not a very hard coding, but we will go through these and talk about it in details. This one, and then we will also having the multi-threading, and then also the takeaway journal stuff we will talk about during our next session. But basically um, it is you can do it like other cases. You can do it in 2 ways. You can do the video slides, and then you can answer your questions in your own words, explain how time quantum value and context switching. We did not cover all these things, so we will talk about it in the next session. But basically, I mean, day after tomorrow on Wednesday, we will have time to discuss all these things in details. We will also have time to do the quizzes. But what I'm asking you to do before we even start our next class, sometimes find some time to fill out the attendance quizzes. I see that many of you are missing on the attendance. Uh, some of you were present in the class, but then I see you are not marking your attendance quiz. This is not good for you because you are missing all those attendances. This is super important. So mark those quizzes and mark those in time. Otherwise, if you are marking it late, then you will be tardy. So that's not good. And also start your discussion process regarding the processes and threads. Put your information, like give uh, give a response, and then give response of the 2 discussions happening in the threads. So that will complete your assignment for the discussion. These are easily claimable points, so don't miss on it. So this is super easy, and try to knock this exercise, the discussion, as well as the attendance quiz as fast as possible, so that you are ahead in the points tally. So you can focus more on these exercises. So I think these 2 we have already discussed today. So we next day we will start our discussion with this one. We will do more hands-on than the theoretical lecture. So theoretically, you can we will touch base on different aspects like the like the scheduling algorithm. I mean, all those things. We will basically touch base those things, but we will spend most of the times in the hands-on on the threads and multi-threading. These two things we will be emphasizing more in the next class. So be prepared for that. If possible, start doing some preview of whatever is given and do some research online. You will find a lot of resources regarding these programs. Like for example, this is a simple Python code. If you look at the code, you will see that, I mean, it starts with importing a package threading that is related to the threading feature in the Python programming language. Then, I mean, it is kind of a process, threaded process. It's an example of a threaded process. Then you do the, I mean, the function to print the numbers, and then you define the function to print the characters here. Then you create two threads, basically the print numbers and print characters. Then you start these two threads, and then you wait for threads to finish, end of the program, and just you you should try to understand what it is going to do for you. So you can see here that you are basically defining two functions. There is nothing um, problem in that. Two different functions. Now you are creating two threads. Now each of the thread has a target. This thread, the first one, thread one, is targeting this function. Thread two is targeting this function. So then you start both the threads. Then you should expect the threads to print these numbers, I mean, these numbers and these characters. And then at the end, I mean, whenever, I mean, thread one join means you are waiting the threads to finish. All the threads are finished, then you should see end of the program. So your expectation should be you will start seeing the numbers, stream of the numbers, and then the stream of the characters. There is no guarantee how they are ordered. Then you should stop. I mean, you should wait for until all the loops are executed, and then you should see at the end the print word end of program. So that's what you are expecting. So next you should run the program. I will show you how do you run the program. I'm just giving you a preview of what is expected here. Then you repeat the step 2 and step 3 again. Um, I mean, so basically, what is the purpose of threading module in Python? So that you can start researching about those. Although I will discuss it in detail, but I want you to get ahead of me and start exploring these things. And also, why do you think the output is different between the run times? I mean, if you run it different times, you will see different levels of outputs. Why? So those things, because I mean, when you do the threading, there is no guarantee which one will execute first, which one will execute next. So we will see that. So let's start brainstorming about this, and we will do this exercise together during the class. What we want to do here is that we want to get a proper mixture of hands-on and theory. The theory is important because you have to have the concept, but the hands-off is kind of more important because it's basically you have to understand the threading. The operating system does not, I mean, as I said to you, operating system is representing the levels of abstractions or extended machines. So basically, when we discuss theoretically, we were we are extracting a lot of things. We are not going into the detailed implementation. But when we do the coding like that, this is a very simple code. There is no, I mean, sophisticated coding involved here. But we will learn how does the threading work. Because when you run the Python program, basically it is a single process, single program or single process. underneath a single process, you define two threads. So this is an example of multi-threading. Two different threads are running under a single process. And then you will see how these processes, how these threads are executed, and how do you see the results and how do you interpret the results. That's the main purpose of this exercise. So I've explained a lot, gave you the preview. So if possible, what I want you to do is go through the program. DEF in Python actually, DEF stands for defining a function. And then for is some repetitive loop. Like if you want to repeat some work over and over, then you use the for loop. And the syntax of the Python is putting those colons around. So get yourself familiar with the structure of a Python program. I'm not asking you to learn the whole language. Just get yourself familiar with the program, and then we will discuss about this program. I will we will be using some IDE, Visual Studio. Sorry, not Visual Studio. The Visual Studio Code to execute the Python program. I don't know how many of you already went through the Python lessons, but we will do some preview of the Python. That will be a bonus material in this class, and we will go through that. So if you have not installed any Visual Studio Code, we will be doing that too during the class. So that's pretty much our plan for the next class. So before we conclude today's class, do you have any questions for me? Any suggestions like I should go slower, I should go faster, um, or more technical stuff than theoretical stuff, or the otherwise? If you have any suggestion, do let me know. I mean, when we do the class, it's easier for me to adjust the pace along with your requirement. We can adjust everything because our only purpose is to learn how do we basically implement, and how do we uh, use the operating system. So we will learn the commands, we will learn the processes, threads, simple programming model. We will learn all of these things. So let me know if you have any input, any feedback, and also feel free to set up any time with me.
Let
Any
me ask
questions?
one.
Yeah, sure. Go ahead,
Uh,
please.
I was when you was talking about the hands-on chapter 2 processes assignment,
Mm-hmm.
I was kind of lost because I didn't know which one you was on. But
Oh,
when you have to it says store the details of all processes owned by root and a file called root processes.
mhm.
Uh to store it, are you just taking a screenshot of it, or if I follow number 1 and 2, it'll store it
Yeah,
in there
okay.
for me?
Okay, that's a very good question. Yeah, I know this is, if you look at it for the first time, it is confusing. So what I did here is I fired up my Linux Mint, the Mint Linux. Then I was exercising some command ps minus ef more. So sorry, ps, it should be ps.
Oh,
So this one. Now you will take screenshot of this one to identify the root process. See, these are the root process. PPID equals 0.
oh yeah.
These are the root process, and other processes are not. These are the root processes that triggered just after booting the system.
Oh,
But other processes, non-zero, these came in place after the system is booted. So
oh.
that's the first thing. You have to take the screenshot. Then I did that file managing system. So what I did here, I did ps minus ef. Then I do a pipe. The pipe represents the filter. Then I do grep. Grep is finding a pattern. Grep, and I put root. So I want to find out anything with the user ID root. So I put grep root. Then I put redirector operation. So that is greater than operator is called the redirection operator. Then I do root processes 1. So that means I am doing this command. This is not a screenshot. I am doing this command. Then I'm adding a filter. What is this going on? Oh, okay. Whatever. I'm doing this command. I'm doing the pipe. That means I'm adding a filter. I put the grep command. Then I'm redirecting the result of this whole command to this file. So once I execute that, enter. Once I execute that, I should be able to see this file in this folder. So if I do that and then root processes 1, you see it here. This file is created. Then if you want to see the content of the file, do more and then you see all these things. So from your perspective, what you should do, I mean assignment perspective, you should execute this command. This is first thing. Take a screenshot of this one. Then once you execute it, then you do ls minus l. Then you will show that there is a root process 1 created. Take a screenshot. That will indicate that this file is created. Then you do more root processes 1. That will show the content of the file. Take another screenshot. That is what is required. Now, okay. Now you will shut down the system. Basically, you will go there, do a right click, and then you stop the system, power off the system. I'm not doing the power off, but you will do that. Once you power off, you will again power up the system. Like you have to start it. So once you start the system, then you go back to this command line, I mean this terminal, create a new terminal and do exactly the same thing, but now do processes 2 instead of processes 1. So now at the end of that, you will find 2 different files, root processes 1, root processes 2, and also my processes 1 and my processes 2. Then you do diff, root processes 1, root processes 2. So that will show the difference between these 2 files. Diff, yeah, diff is a Linux command that shows you the difference between 2 files. This is the way Linux understands it. So if you enter it, you will see 2 sets of lines. One is with less than command. So you have root process 1, root process 2. So root process 1 versions are there with the less than command. Then you have a greater than command. You see here, this line, this is the first line. This line and these lines are different. It just says that these lines are different because basically this is the, this is 1C1, that is comparison between these 2 lines. That's what it says. So that's pretty much it is. So that you are going to show. Basically take a screenshot of the first few lines. That should be enough for your assignment.
Thank you.
Yeah, that's pretty much it is. Yeah, that's a very good feedback because I did not know that, you missed all these points. So this is important. So that's always provide feedback like that. Then it will be easier for me to catch up with whatever issues you are having.
And then like on the second one, when you do it, you have to kind of do the same thing with the root process, but instead put like Shiloh and then my process there.
Exactly. Yes. In my case, it is deb, and I do my processes, but in your case, it should be silo. So that
Oh.
is very nice. Yeah, that's what you want to do.
Because
Yes.
when I seen it at first, because I had printed it out like yesterday, I
Mhm.
was thinking when it said store it, I didn't know how to store it into the terminal. I just thought it
Mhm.
meant like just take a snapshot and compare it with like two different snapshots or something.
Yeah, yeah. I mean, that is confusing, of course.
Uh, and then the part about scroll, about above that, scroll through the list and take note of the user command
Yeah. So
percentages
that's pretty much scrolling is done by here, for
going up and
example.
down.
So basically, you have to do more. This is the Linux way of scrolling the things. When you do the mode, that means you see here, there is a pagination. So if you enter, you will see more lines to it. So that is the scrolling basically.
And then I
You are
just
not,
have to.
so you are not scrolling using your mouse. So you are scrolling by hitting your enter button. Yeah. So that's the command line scrolling basically. It's little different
Yeah,
from, yeah.
I
It's
got
little
understood this. Oh,
yeah.
no, I'm sorry.
Yeah, it's little different from Windows world. But it's I mean, if you start doing it, you will be more like familiar with this process. And if you do a space bar, it will be a page long scrolling. So basically, you
Oh,
are paginating. Space bar is for pages. Enter is for record by record, one record at a time. If you enter space, then one page at a time. That's the difference.